only the survivors are here today after so much mathematics last Friday. Today I want to talk again about K-theory. We looked a little bit at K-theory some time ago, in the second lecture perhaps, and so I want to return and discuss K-theory again, and the famous Kohn-Kasparov isomorphism, Kohn-Kasparov map, first of all, that I'm supposed to be talking about, and Dirac operators, a little bit more about discrete series. We'll talk about these things today. And some of the old things, my favorite picture. The picture will come back later today as well. Okay, but first of all, just some abstract ideas concerning C-star algebras and Hilbert modules, C-star modules, I guess we're calling them. So suppose you have a C-star algebra A. Eventually, it will be a group C-star algebra, but not at the beginning. And let's remember that we discussed at some points C-star modules. Over C-star algebra, so for example, over A. And so there is a definition. The critical idea is this, that first of all, this is a right A module. You can multiply elements of E by elements of A on the right, and there's an inner product, which is conjugate linear in the first slot, even with respect to the action of A, and then linear in the second slot. And it's valued in A. And it satisfies the axioms that you would expect of an inner product, as in a Hilbert space inner product. In fact, if A is the C-star algebra of compact operators, this is just a Hilbert, a C-star module over A is just a Hilbert space. We talked about compact operators on such a module. So this is a C-star algebra of operators, and it's generated by elementary operators like this, rank 1 operators, if you like, which send V to the following thing. Well, you pick some vector V1 in E, and then you just do a multiplication operation like this. If you think about it, that's a well-defined operator from E to E, assuming that V1 and V2 are in E. And the linear span of these is a star algebra, and the closure is what is called the C-star algebra of compact operators. And we also talked about what we meant by Fredholm operators. In both cases on E. A Fredholm operator is just an operator which is invertible, modulo compact operators. And the word operator assumed the existence of an adjoint with respect to this inner product. That existence is automatic in the Hilbert space case, at least for bounded operators. And here you assume it. Okay. And then we made a definition which we didn't really explore. So we defined the K-theory group of A. I'm going to concentrate on what's called K0 of A, and it's just the set of homotopy classes of Fredholm operators. On which module? Well, on any module. So we discussed what homotopy means, and it's possible for one Fredholm operator on one module to be homotopic to a Fredholm operator on a completely different module. There's a very flexible notion of homotopy classes. This particular notion here is due to the idea here, the definition. Due to Kasparov. It's a very beautiful idea. Atiyah noticed a long time ago that homotopy classes of Fredholm operators are related to K-theory, and Atiyah had this rather beautiful way of making that precise and very general like this. Okay, I don't think we looked so much at examples, except maybe it's some very, very simple case. So let's study this in a bit more detail now. But if A is the complex numbers, then one thing we can say is that this is just the integers via, this isomorphism is via the usual Fredholm index. So the homotopy class of F goes to the dimension in the usual vector space sense of the kernel of F minus dimension in the usual vector space sense of the co-kernel. And it's part of the theory of Fredholm operators that these are two integers, two finite quantities that we're taking the difference of. Okay.
For the definition of K0, don't you need stabilization?
Don't I need stabilization? No, because I'm assuming here that I'm not choosing any particular module. If I wanted to fix a given module and only work with operators on that given module, then I would have to choose a sufficiently large module, somehow a stable module. But that's not relevant here. And A, the C-star algebra, does not have to be a stable C-star algebra. Okay. If A is the C-star algebra of continuous functions on a compact space, then the object that Kasparov defined is isomorphic to something that was defined much longer ago by Atiyah and Hesselbrook, the so-called topological K-theory, Atiyah-Hesselbrook K-theory. That this consists of formal differences of vector bundles on X, and a vector bundle is a continuous family of vector spaces. Roughly speaking, an operator in the second case is nothing but a family of ordinary Fredholm operators, as in the first case, parameterized by X, and you can, roughly speaking, associate to such a family the family of vector spaces, which is the family of kernels. That's, roughly speaking, a vector bundle, and the same for the co-kernels. And in that way, you can, roughly speaking, associate to any Fredholm operator in this sense, that sense up there, you can associate a difference of vector bundles. Now you have to worry about the details. It's a little complicated. But this is the result. There's a very beautiful map in, I think I mentioned this, in this direction. If I have a vector bundle, I can build a Hilbert module, a C-star module out of it just by taking the space of all sections. That is an example of a C-star module. And then I can take the zero operator from that space of sections to the zero module. That turns out to be a Fredholm operator, and so that gives a map from here to here. That's a perfectly respectable and well-defined and rigorously defined map, and it turns out to be an isomorphism. Okay, so those are some easy examples. I want to dwell on a different example. Oh, maybe I should say before I go on, this is really all I'm going to say about A1. So we defined K0, but there's also a group K1. Where is it? Oh, right here. There's also a K0, a K1, which is just homotopy classes. All you have to do is add a little clause here, self-adjoint. Fredholm operators. On C-star modules over A. And the groups K1 and K0 should usually be considered together. However, I'm going to focus just on K0 in this lecture. And here's an interesting example of the plane. And this is an excellent example for our purposes. It will illustrate what we want to achieve in group C-star algebras, as you'll see. So I want to give you an example of a very interesting Fredholm operator over this thing. And the Fredholm operator looks rather pathetic. So there's a sort of fundamental Fredholm operator, which we'll spend the rest of this lecture studying and generalizing and studying some more. I didn't mention it here, but these Fredholm operators can map one C-star module into a different one, and I'm trying to, from here on, get into the habit of allowing that possibility. In this particular case, E0 will equal E1, but that's just a sort of coincidence. So the modules will just be copies of the algebra, viewed as right modules. And I mentioned this before, but let's do it again. If the way you define the inner product in this situation is just like this, so that is a C-star algebra valued inner product, and it satisfies all of the axioms, which I didn't write down this time. That's the definition. What's the operator? Well, suppose I have a function in here, which is here. Well, all I'm going to do is multiply this function by another function. That's really all you can do. And the function I'll multiply by is just x plus iy. That's the idea. There's a little detail here that you have to worry about, which is that if you have a function like f, which vanishes at infinity, and you multiply it by z, by x plus iy, it may no longer, it'll still be continuous, but it may no longer vanish at infinity. So this is unbounded, or if you like, not everywhere defined. And this we'll see several times, this problem of something which is not everywhere defined. And there's a trick. There's a trick to coping with this, which is to replace f, or if you like, this function, call it, by its so-called bounded transform. We're studying K-theory, we're studying homotopy classes of Fredholm operators, and I just need to invent some way which converts this operator into a bounded operator without destroying somehow its essence. For example, I wouldn't want to replace this function by the constant function 1. That would be too crazy. But here's a reasonable way of doing it. So what I'll do is I'll just take the function, multiply it by its adjoint like that, and then take the square root and divide by the square root in this sort. So if you like, in function language, just make the function bounded in this way. So this is a function which at infinity is equal to, not equal to 1, but equal to 1 in size, so equal to a function of modulus 1. This is a minor detail, and I don't want us to worry about it too much, so this is the only time I will mention it. This is a very beautiful formula. This is not such a beautiful formula, but let's just continue for this one time. After you've made this modification, if you take f and you multiply it by its adjoint, what you get, so I'm taking this function and I'm multiplying by its adjoint, so there's going to be this quantity squared after I've multiplied by the adjoint, and then what am I going to get? F times f star. Well, I'm going to get f star f 1 plus f star f inverse, like that, which is the same thing as 1 minus, oops, maybe I should say, too many f's now. Let's say the f that we've made bounded is equal to the f which is the original f. This whole thing is bounded. Here's the original f. So now this is 1, what is it? It's 1 minus 1 plus f star f inverse. So that's 1 minus the operator here of left multiplication by a function in A on this A module, and that's 1 minus a compact operator. So this is a Fredholm operator, according to the definition. Look at its invertible modulo compacts. You need to know that left multiplication by an element of A is a compact operator on such a simple Hilbert module as this. That's an easy thing to check. And now this is a Fredholm operator. Of course, you do the same for f star f. I mean, ff star. So it's not much of a Fredholm operator if you're used to thinking of Fredholm operators. If you're an operator theorist, you might think of the unilateral shift as being your favorite Fredholm operator, an operator of index -1. Here, the operator is sort of spread out over R2. At any point of R2, it's just a just a number, and so it is a Fredholm operator, but it's made up out of a family of operators from a one-dimensional space to a one-dimensional space. Think of E0 and E1 as being associated to fields of Hilbert spaces over R2, and the fields are all one-dimensional. So it's possible to create Fredholm operators out of finite dimensional quantities, as we're seeing here. And somehow the idea of Fredholm operator is capturing something different and interesting, namely the topology, in this case, of the plane. So here's a fundamental example. So it's a theorem, not, in this case where we're just dealing with a plane, not hugely difficult, but the theorem is that this freely generates the abelian group K0 of A in this particular case. All right. And so this is an interesting and strange example. K-theory, as you see from this formula here, is very topological. This is some cohomology theory. This is the zeroth group of some cohomology theory on the space X. And so K-theory has a strange homotopy-theoretic, cohomological character, despite being built in an operator-theoretic way. And in the case of the plane, here's the construction, which is somehow very algebraic of everything that is in this group. And there's a generalization of this R2, which is I've written over there, to Rn. Any n will work. I'm going to stick to the even case. Case where n is odd is related to this odd group, which I promised not to say anything more about. And so we'll just think about the even group here. So what I mean is I'm going to study the C-star algebra, which is the C0 functions. And in order to do it, you have to somehow abstract the essence of this and then generalize. And that takes a little bit of thinking. And it's one of the reasons that I tried to prepare us by defining E0 and E1 separately, even though they are equal to the same thing. So here's what was eventually decided by the experts who study K-theory. Suppose I have a collection of self-adjoint matrices, of course square since they're self-adjoint. And suppose these matrices satisfy the following algebra. First of all, if I square any one of them, I get the identity. And secondly, here's the interesting formula. These matrices anti-commute with one another. Suppose I found such a collection of matrices. I want n of them, and in case of n equals 2, it's not hard to come up with examples. For example, you could start with this fella. That's a matrix whose square is the identity, no problem. Of course, the identity matrix is also a matrix whose square is the identity, but the identity matrix is not going to anti-commute with anything. Here, however, you have a chance of making some anti-commutation. Here's another one which will do the job. Has to be self-adjoint, so if I put the square root of -1 in the bottom, I have to put minus the square root of -1 in the top, and there you go. There are a couple of examples, and now you do the matrix multiplication, and you work it out, and you see indeed they anti-commute. All right, what are we going to do with such things? Well, first of all, a little algebraic lemma. Think about it, you can do it with matrices of this size, 2 to the n over 2 times 2 to the n over 2. Remember, I'm assuming that n is even. But you can't do it with anything smaller. In this example, n over 2 is 1, so we're talking about 2 by 2 matrices. This is the minimal size. Now let's define one more matrix. Just by multiplying all of the other ones together. And adjusting by some factor, which is the square root of -1 to the nth power. So it's either, well, it's one of the powers of the square root of -1, I minus I plus or minus 1. And this is another matrix satisfying exactly the same algebra as all of the other ones. And we're going to use it in a slightly different way from all of the others, which is why I treated it separately. So continuing the definitions. I'm going to build a Hilbert module over the C-star algebra of functions on Rn, and I'm going to use this dimension for the purpose. And what I'm going to do is take functions from Rn into vectors of exactly this minimal size. Like that. So on this space of functions, these matrices act. These are vector-valued functions, and matrices act on vectors in the usual way. So this is a module over the matrix algebra of 2 to the n over 2 by 2 to the n over 2 matrices. It's also a module over functions by pointwise multiplication. So now I want to break up this space according to the eigenspaces. Of the final matrix gamma over there. Okay, so the indices here you should think of as being, if I call the index here j, then we're looking at the -1 to the j eigenspace. Look better. These are the two eigenspaces that are around. See if we can squeeze it in here. And we can define an operator by some generalization of this formula here, namely f applied to a function at a point x1 up to xn will just be, well, I'm going to multiply by x1 gamma 1 plus xn gamma n times f of x1. And if you study this package in this context where n is equal to 2, and you compare it with what's up here, you'll find it's exactly the same. It really is exactly the same. It's rather beautiful, and once you get used to it, it's rather simple too. Of course, it takes some getting used to all of this stuff, unfortunately. Now the theorem, which is basically the famous Bott periodicity theorem, is as follows. This is a much harder calculation to do this in general. The theorem is that indeed this Fredholm operator defined in this way freely generates this K theory, where A is C0 1. And although we're doing some sort of linear algebra here and some sort of C-star algebra stuff elsewhere, this is very rapidly reduces to a completely different statement, which is that if you take want to calculate the homotopy groups of GLN, the complex numbers, where n is really, really big, n should be really, really big compared to j. Actually, that's an exaggeration. N should be something like j over 2, at least j over 2. Then these groups, it's a wonderful theorem of Raoult-Bott. Let's get this right. These are Z, J is odd, 0, J Z. There's a statement in homotopy theory, which is exactly what I wrote down there. And in fact, it's really the same, basically the same as this statement involving homotopy classes of Fredholm operators. And the translation from one to the other is relatively elementary. I shall not show it to you. But basically, we're talking about the same thing when we're discussing Fredholm operators over a commutative C-star algebra we're talking about the same thing as homotopy theory of groups of matrices like this. I shan't explain the connection, but there it is. All right, so when you study these Fredholm operators, you're entering into the realm of topology. And if you know something from topology, for example, this wonderful theorem of Bott, then you can translate it into some statement about Fredholm operators. For example, this statement up here. Oh, sorry. This, I guess this is the n equals 2 case of this theorem here. So that's a very strange and interesting and beautiful story. And it's related to what we're supposed to be doing in these lectures for the following reason. Let's take the C-star algebra of a group, and not any group to begin with, but the group R2n. I could consider R2n plus 1 as well, but then I'd have to tell you more about odd K-theory, but we'll just stick with even K-theory. There's an odd version. You can probably guess it immediately, which is related to all of this. But anyway, let's consider this particular case. Of course, this C-star algebra is isomorphic to the one we've just been discussing. It's just the same via the Fourier transform. We took a look at that at the very beginning. And so we can use the Fourier transform to translate everything we were just talking about, including this strange encounter with homotopy theory. We can translate all of that into the language of group C-star algebras. So we can translate this into a statement about group C-star algebras. In the Sabelian case. And it's very, very interesting. First of all, here's a definition. We had some crazy formulas. Here we go, some crazy formulas here, defining a certain operator on the module of all functions on Rn. And what this operator is, well, it involves matrices and vectors, but basically what it is, it's multiplication by a polynomial function. In fact, a polynomial matrix-valued function, a linear polynomial matrix-valued function. But that's what it is. And when you convert such a function using the Fourier transform, multiplication by a polynomial gets converted into an application of a differential operator. It's a fundamental fact that if you take a function and take its Fourier transform and then multiply it by x, that's the same thing as first taking the function and then differentiating it and then taking the Fourier transform. Fourier transform interchanges multiplication by x with differentiation by x. So you can apply that in this situation here. And what you end up with is the following particular operator here. Well, there's the square root of -1. Let's not worry about signs. And then there are the, in fact, too many i's and j's. Let me write the square root of -1 like that. Here we have gamma j. Here we have dxj. This is the so-called Dirac operator. Oh, no. I forgot to say it, but another part of the algebraic analysis of these matrices that you see at the top there is that these matrices are essentially unique. If you have two systems of matrices, some gamma matrices and some gamma prime matrices, then they're in the obvious sense unitarily equivalent to one another. So they basically not only exist in this minimal dimension, they're unique there. And so this operator not only exists, but it is unique, and it has the wonderful property, which is why it's called the Dirac operator, that when you square it, well, if you square it, it's quite obvious that, well, first of all, the square root of -1 times the square root of -1 is -1. And then these gammas, when you square them, you either get 1, gamma j times gamma j is 1, according to the formulas, or you get nothing, because gamma I times gamma j will cancel off the term gamma j times gamma I, the cross term in this square. And what you'll get is just this expression. The Laplacian, or depending on your conventions, minus the Laplacian, depending on which political party you belong to. So Dirac, for physics reasons, was searching for an operator which was the square root of the Laplace operator, and he came up with this algebraical idea of using matrices. And so the counterpart of this theorem, one that's up here, is that the Dirac operator made into a K-theory class just by the very same observations which made this function into a K-theory class. It appropriately viewed, it is a Fredholm operator. This Dirac operator freely generates the K-theory group of C star. All right. By the way, just a little before I erase this little exercise, get you thinking. These matrices are very closely related to, but not exactly the same thing as Hamilton's quaternions. So it's fun to, so that's some, as you know, four-dimensional division algebra with some generated by some elements I and J and K over the complex numbers, and it's related in a very interesting way to this matrix algebra. So what I want to do is take this story here, which is a strange translation, and it involves the Fourier transforms, involves all sorts of crazy things. A strange translation of a theorem in homotopy theory, this famous about periodicity theory. And I want to take this story and translate it one more time so that I can apply it to the groups that we're supposed to be studying, these real reductive groups. At the moment, we're just talking about abelian groups. And in fact, there's a version of this statement and this theorem up here, which is true also for reductive groups, and that's what I want to explain. And in order to do that, I have to go back and study this business here in a slightly more abstract way, not so far away from the theory of quaternions. And that involves the following idea. So the goal is to generalize this thing here, this theorem, let's call it theorem star. To the sorts of groups we've been talking about. It's a very interesting story when you do that. And we hope that something beautiful will happen. At the very least, there'll be some strange interaction between homotopy theory and representation theory. Very surprising. But who knows? Maybe the homotopy theory tools will be useful in representation theory. That would be fun. Or vice versa. So we want to examine to what extent this theorem over there, which is basically a translation of Bott's theorem, to what extent it makes sense in the world of reductive groups. And hopefully, eventually, we'll connect with, you know, this picture that I like so much, and discrete series representations, principal series, and so on. But first, we need to examine these matrices in a slightly different way, or let's just say more closely. As follows. Suppose I have a vector space, just a real vector space, with an inner product, finite dimensional. No C-star modules here, just a real vector space, like Rn, with an inner product. And when we finally get back to groups, this will be the vector space P, which appears in the following way. Every reductive group, remember, is K times the set of exponentials of some vector space of symmetric matrices P. These are the symmetric matrices which exponentiate into G. This is this decomposition of G. Tells you that topologically G just looks like K, and then this topologically looks like a vector space. This is, if you like, the symmetric part, the set of the vector space of symmetric matrices in the Lie algebra of G. This is the skew-symmetric plus symmetric matrix decomposition of this Lie algebra of matrices. Anyway, but for the moment, let V, just be some vector space, and then this is an abstraction of what's on the board behind. This is just the associative algebra. In fact, it has a natural involution. Let me explain how this thing is built. This algebra should be equipped with a real linear map which embeds V into it, or maps V into it. And what we insist is that if we apply C to any vector, and then we square the result, which we can do because we're in an algebra here, then what we get is the norm of V squared times the identity. Oh, I forgot the fact that we'd like this to go into the self-adjoint part. You can study this in the realm of either real or complex algebras, but let's keep our life simple and talk about complex algebras. So what I'm interested in is, if you like, the universal algebra which satisfies these properties. I look at all possible algebras which contain the image of some real linear map from V, which satisfies these equations. And among all of them, I look at the most general one, the one which maps to all of the others, the universal example of an algebra satisfying this set of relations. And the little lemma, it's not hard at all, is that as a vector space, this thing, first of all, it always exists by abstract nonsense, but fact, it's always finite. It's finite dimensional algebra, not very complicated at all. And in the situation where n is even, because we're focusing on that, this algebra is very easy to describe as an abstract algebra. It's just the matrices over n of size 2 to the n over 2. Of course, any such isomorphism, if you think about it, any such isomorphism will take an orthonormal basis inside of V, which is mapped into here, and produce a system of matrices exactly satisfying these relations. So just a little remark. These satisfy our relations that we discussed down here. So this is clearly very much the same thing as what we were discussing down here. Let's keep those for a moment so we can stare at them. So this is the Clifford Algebra of V, and because we're about to try and do some representation theory, I want to describe to you how this is connected to Lie theory, to Lie groups. It's a very beautiful way of understanding what this fellow is. Suppose you have a compact group. Compactness is not really important, but to fix ideas, which is acting on this vector space V in such a way as to preserve, isometrically, preserving the inner product. So, for example, the orthogonal group acts on Rn, the basic example. Okay. Well, if the group K acts on V, then it also acts on the Clifford algebra by means of just the universality of these relations. These relations are preserved under any transformation which sends little v to k of v, because k is acting isometrically. So in a natural way, because the group K preserves these relations, it acts as automorphisms on this universal algebra, and so, which is a little finite dimensional C-star algebra, by the way, I forgot to say that. And because we're talking, I didn't write it down, I think I said it, I'm supposed to be talking here about Lie groups. Because we're talking about Lie groups, we can study this infinitesimally at the Lie algebra level. And it's very interesting what happens. So now let's take the Lie algebra of K. What should it map into? Well, if you like, it should map into the derivations of this Clifford algebra. But a better way of thinking about it is to study the Clifford algebra itself. First of all, the Clifford algebra is a matrix algebra, and every derivation of a matrix algebra is inner. And so, in fact, there's such a map as this. I want to think of this Clifford algebra as a Lie algebra with the usual commutator bracket. I want to look at just a little piece of the Lie algebra, which I'll call the degree 2 part, which I'll tell you about in just a moment. And as I say, I want to think of this as a Lie algebra with the usual commutator bracket. Certainly the commutator of two elements in this Clifford algebra is an element in the Clifford algebra. It's an algebra, after all. And we have to worry about this, too, in just a moment. And this Lie algebra homomorphism is supposed to generate this action. So how could that work? Well, there are lots of ways of saying it. You could conjugate the exponential. So let's give this map a name. I usually call it gamma, but that's no good. Let's call it, I don't know, alpha. Let's call this alpha here. Let's call this beta, something like that. So I could take an element here, I could apply beta to it, and now I get an element of this Clifford algebra, and then I could exponentiate it. It's an associative, it's a C-star algebra after all, so I can just take the exponential series. This is now, as it happens, a unitary element in this C-star algebra, and then I could look at conjugation by this unitary element. This whole thing is an automorphism of the Clifford algebra, an inner automorphism of the Clifford algebra. And of course, it should just be alpha of x of x. So this is the differential. And as for this degree 2 part, this is just the linear span of the elements that I was calling gamma here. Let's just do it this way, more or less. C of Vi, C of Vj. Where the Vi's are an orthonormal basis of V. And another exercise, which is the only exercise you need to do to learn the elementary Clifford algebra theory, is just to check that this is basis independent. And the Lie algebra under commutator. You take two such expressions and you form the commutator AB minus BA. It's again such an expression. In fact, a single such expression up to a sign. The next exercise is a little trickier, but it's not so difficult. What is beta of x? If it's unique, well, surely we can find a formula for it, and indeed we can. Once you've settled on a basis like this, the formula for beta is this, or it's minus this. I worked it out before I came. I got it right. It's some strange, crazy formula, but it's there for a reason. As I said, this algebra is not hard to compute. It's just a matrix algebra. Let me write this in a sort of sexier way as just the endomorphisms, linear endomorphisms of some complex inner product space S. So S is just a finite dimensional Hilbert space. And if you put this together with that, you get a representation of K. All of a sudden, you get to do a little representation theory.
Excuse me. What is this VI?
So K is acting on V. It's a very good question. Here. So if you like, this is the usual thing, the derivative t is equal to 0 of x of tx which is an element of K applied to the vector. So it's the infinitesimal part of the action. Thank you for asking a question. More prizes for you. I keep forgetting to bring you your prize. And in this way, you get a representation of K. And hence, there's an asterisk here, a footnote, but I'm not going to go into the details of that. A unitary representation, finite dimensional unitary representation of K. As you know, whether or not you can exponentiate a Lie algebra representation into a Lie group representation, there's a small obstruction coming from the fundamental group. If K is simply connected, you get this. If it's not simply connected, there's a small detail. And let me assure you that the experts have taken care of the details. And it's not always true that you get a group homomorphism. But if you don't, people know what to do instead. You always get a group homomorphism from some double cover of K, and people can work with that double cover. All right, so a little bit of representation theory here. Okay, so this is what's called a spinor representation, or maybe I should say. So we could take V to be Rn, in which case we could take K to be SON. And in this way, you get what's called the spin representation of, well, it's certainly a representation of the algebra when you attempt to exponentiate it. This is a perfect example of a situation in which there's an obstruction. It's a representation of spin n, which is some double cover, in fact, a unique, simply connected double cover. So the spin representation, as I've defined it here, is not irreducible. It's a direct sum of two irreducible representations in the case where n is even, which is what we're assuming. So you have two spin representations, a positive spin representation and a negative spin representation. Okay, and here you have the more general. So a little bit of Lie theory here. The spin representation is very fundamental if you want to understand all representations of the orthogonal groups. There are some standard representations that you get by letting orthogonal groups act on Rn and on exterior powers of Rn and stuff like that. But to understand the full story of the representations of SON, you also have to worry about these spin representations. Okay. And all of this is supposed to be a prelude, just an introduction to this problem of generalizing this dot periodicity result to a reductive group. We need some stuff. It's all about compact groups, basically, and some interesting objects pop into existence, the spinners and so on. And okay, now let's try and see what this all has to do with C-star algebra groups. So far, so good. So now let G be one of the groups we've been studying, real reductive group. everything that I'm about to say can be understood in a high degree of generality. So I'm going to make some hypotheses here. They're not really necessary, but they simplify things. So I'm going to assume that the group is connected. I'm going to assume that it has compact center. Remember, if it doesn't have compact center, it's always a product of an abelian group with a group that does have compact center. So it's no big deal to assume it has compact center. And if it's not connected, it's almost connected. It has only finitely many components anyway, so these are not terribly important things. And now I'm going to assume one more thing, which is what's called the equal rank condition. And again, this is to make my life as simple as possible, maybe make your lives as simple as possible too. So what does equal rank mean? So this is the condition which guarantees that the group has these famous discrete series representations. It means that if T is a maximal torus in K, then T is basically maximal abelian in G. So T, centralizer of T, of T in G is compact. This is the situation, remember, in which it's not the case that all of the representations of G can be explained by transferring from some smaller group. This is a situation in which G has some of these mysterious discrete series representations which cannot be explained in terms of smaller groups. And it's not, none of these hypotheses are necessary, but they simplify matters. And one of the ways in which you see a simplification is that if you do this decomposition that we were discussing a moment ago, then the dimension of P is even. Do the calculation and see what's going on, invent some symmetry to guarantee even parity, and it's not so hard. Let's pick a group completely at random, SL2, and let's examine what's going on here. K is SO2, which is one-dimensional, and SL2R is three-dimensional, and 3 minus 1 is 2. That must be the dimension of P, and 2 is even, so yeah, it works out. Good. And so we have, if we're lucky, this spin representation coming from the Clifford algebra that you can build out of the vector space P. So K acts by conjugation on P, the symmetric matrices in the Lie algebra. And so we're in this position that we were discussing here, this crazy formula, blah, blah, blah. There's a small obstruction. Some fundamental group issues in general have to be considered. But for example, for SL2, they don't. Oh, I wanted to give some example here, maybe another example. Mind if I'm just going to stick another example in here. Let's, I guess it is this example when, almost this example when n is equal to 2. But in this example, I want to do something slightly different than what is appearing above. So K will be SO2. But the way in which K acts on V will be a little bit different. So if I have a matrix cosine, sine, sine, cosine like this, acting on a vector, I want to define the group action not in the usual way by matrix multiplication, but by squaring that. So that will be cosine minus sine, sine cosine squared. Now, just the usual matrix multiplication. So I'm defining here some new action of SO2 on R2, which is just the square of the old action. And I'm allowed to do that because SO2 is abelian, so it's still an action. And so in this situation, you can play this whole game, and now you get an action. Of SO2 on S, which is isomorphic to C2. 2 to the n over 2 in this situation is 2. And it looks like this. You can calculate. So this real matrix real orthogonal matrix will give rise to a unitary 2 by 2 matrix acting on here. And what the action is just cosine plus I times the sine of theta here and cosine minus I times the sine of theta here. If I didn't put the square in here, if I just took the standard action, then I would have to take the square root of this complex number, and that's not well defined. And this wouldn't be a real action. It would be an action of some double covering group. And in this particular case, everything works out. This is another excellent exercise. Okay, and by the way, that's the reason I mentioned, the reason I was reminded about that is that that's exactly what happens in the case of SL2R. When you work out the case of SL2R, as we're doing on the left-hand board, it's this particular representation. Anyway, we get from this Clifford algebra some representation on a certain vector space of dimension 2 to the n over 2, where n is the dimension of P, and this is what it is in the case of SL2. Okay, great. And now we can build a Dirac operator. In fact, we can build several Dirac operators. Suppose I have an irreducible representation of K. If we were in a situation where we were in this footnote territory, it really should be an irreducible representation of some double cover, but we're just ignoring that detail. And what I want to define here is a Dirac operator, and it will depend on sigma. So there's a new parameter here that we didn't see in the case of Rn. And it's a summation, and it's a summation over an orthonormal basis for the space P. And here's what we're going to do. We're going to take sigma to 1. I'll tell you what 1 is in a moment. And finally here we're going to take this Clifford algebra C. And the only question is, where does this crazy thing act? Well, this thing is a Fredholm operator on, okay, drum roll. here's what we're going to do, keeping in mind what we did in the abelian case. Basically, we're going to act on the C-star algebra of G. Remember before we acted on the C-star algebra of Rn? Except we have these Clifford algebra elements, so that's easy. They're going to act on the space S. And as for this one, it's just going to be the identity operator on the Hilbert space of sigma, like that. And finally, we're going to take the k fixed elements in this gigantic sum here. Where k acts by, say, left translations. And as for these derivatives here, they also come from left translations. So I'll just take f and I'll just move it a little bit by x. I guess these are the obvious differentiations corresponding to the action of G, or of the p part of G. So you can't always take such a derivative of some f which is in the C-star algebra. This is not defined everywhere, but neither was the operator defined everywhere in the very simplest case of Rn. And so one has to do this bounded transform trick in order to assure that this is well defined. Okay, so you have to consult with an analyst to see that this expression really does make sense and really does have a bounded transform and does define it in some sense a Fredholm operator. This is an example of an unbounded Fredholm operator, a so-called regular Fredholm operator, and by bounded transform it gives an honest Fredholm operator. There's the formula. And let's just examine what's going on here. This thing is a C-star of G, C-star module over reduced C-star algebra of G. In other words, among other things, it has to be a module over the reduced C-star algebra of G, a right module. It should be possible to multiply by C-star of G on the right. Well, no problem, because all of this differentiation is happening on the left. So all of these operators are linear for the right action of C-star reduced G. And this is a C-star of G module. There is an inner product, which is just the standard inner product here and the standard Hilbert space inner product here. And here it's the usual inner product on a C-star algebra. A1 star A2 that we saw before. So this is a C-star module. This is an unbounded Fredholm operator on it. And if G is Rn, this is exactly the construction we had before. G is Rn, then, for example, realized as the positive diagonal matrices inside of GLNR, made into a reductive group in that way, then, well, it has no k. It has no k, so you can forget about V sigma because k is the one-element group. It doesn't have any irreducible representation except the trivial one. So this goes away, and this goes away. The spin representation stays. So we still have these gamma matrices of Dirac. And the C-star algebra of G stays. Under Fourier transform, this is just matrix, or rather vector-valued functions on Rn. The operator under Fourier transform is just multiplication by some linear polynomial. It's exactly what we had before. When G is Rn, this is exactly the thing we had before, which rather mysteriously and miraculously was related to homotopy theory, to the Bach periodicity. But now we've done it in this strange way, which also includes some representation theory of this compact group. We have this extra parameter sigma, this discrete parameter sigma. But otherwise, it's exactly what we had before. By the way, at the other extreme, if G is compact, sort of a trivial construction. The actual operator that we're discussing is the zero operator because there are no directions p in this decomposition, wherever it is, g is equal to k plus p. There is no p, so there is no orthonormal basis for p. D is the zero operator, okay, and S is the trivial one-dimensional vector space. It's not a completely trivial construction because V sigma is still there. Okay, and what we're doing is we're picking out just isotypical parts of the representation space of C star of G according to the Peter-Weyl theorem. I should say trivial, but not zero. The Dirac operator is zero. If you think about it, it's the zero operator from C star G tensor V sigma k to zero. It's not the zero element in the K theory when you study this Fredholm operator. It's this Hilbert C star module here, this C star module here. Okay, so two cases. In both cases, let me go over here. So we're reverting to the old custom. No breaks, no vacations for anyone. We work until we cannot work anymore. We obtain, and there's an asterisk, like there was before. And the asterisk has to do with the fundamental group of K is used. Has to do with this spin representation, whether or not it's a real representation. And if it isn't, what I'm about to write down has to be adjusted very slightly. And, okay, there are other hypotheses there also. Each time you have an irreducible representation of K, so this is the free abelian group. On the set of irreducible representations, you can build a Dirac operator, which is a Fredholm operator, and so it has an index, and it lies here. So this is the index map of Kahn and Kasparov. Actually, Kasparov. And the conjecture, of course, which is now a theorem. The conjecture of Kahn and Kasparov, which was made a theorem. First of all, by Wassermann, although he never gave the details, and then by Laforgue, who did, in a completely different way. This is an isomorphism. And the examples which you can work out by hand of course it's a theorem all the time, but you can work out by hand that this is correct when G is Rn or G is compact, as indicated over there, just by calculating what these operators are. Oh, and using Bott's theorem, that's important. Very strange statement, mixing a number of different things together. And what I want to do in the remaining time, which is still a little bit of time, is discuss this this conjecture in the light of discrete series representations. So this conjecture, this theorem, would not be a theorem. It would not be correct if Bott's homotopy theorem was wrong. And it also would not be correct if Harishchandra's calculation of a classification of the discrete series was wrong. It covers a lot of territory all at once. It says something about homotopy theory, and in the abelian case, and something about discrete series, among other things, in the in the general case. By the way, it doesn't say anything. If you think about it, the statement is sort of trivially true in the compact case. It's this map, this Kohn-Kasparov map is basically the identity map from R of K to R of K in the compact case. It's not saying something interesting like the Weil character formula is. It's saying nothing in the compact case. But in other cases, it's saying a great deal. And so it's very striking that it could be true, that some single statement could tell you something about homotopy theory and something about representation theory, discrete series, all at once. But here it is. Okay. So going back to what we understand about representation theory, if G has compact representations, well, we made a whole bunch of assumptions about G, including this equal rank assumption. So in fact, it does, just because we're focusing on that case. Strictly speaking, this is not an example, because this is not in the equal rank territory, but the definitions all apply to it. As I say, there is a Kohn-Kasparov conjecture for any G whatsoever. Each time you have one of these things, there is a class. Let's call it square bracket pi. Because after all, according to the definition of compact representation, the C-star algebra of G is the compact operators on H pi, an ideal isomorphic to that, plus the kernel. It's a fact that if C-star algebra is the sum of two other orthogonal ideals like this, then the K-theory of this thing is the K-theory of the compact operators plus direct sum, that is, the K-theory of whatever this thing is. And the K-theory of the compact operators, well, compact operators are isomorphic in this category of noncommutative spaces, just to see. The K-theory of the compact operators is just Z, and so there is a canonical generator. It lives here. And so it's very natural to ask, how do these relate? Or how are these related? Class is related to the Kohn-Kasparov map. And so in the remaining time, I'd like to tell you something about that. Let me see what I need to say. I'm trying to make a point that this statement is very, of Kohn and Kasparov, is very striking and surprising in the strange way it sweeps across representation theory and homotopy theory all at once. It's hard to think of another statement quite like it. And, but now we want to see what it all means in some special case. And I'm going to start with something that I tried to reach last week, just squeezed it in, which is this formula of Harish-Chandra. Call it his trace formula. And when Harish-Chandra proved this, he did not prove it using the language that I'm about to write down. He proved it using techniques which are similar to the ones that I described in the first half of last Friday's lecture, something like that. I tried to discuss two big theorems last time, and this was the first. This was the second, but Harish-Chandra proved it like he proved the first one. But here's what it says. It has to do with the special trace functional which exists on the C-star algebra of G, which takes an element in the C-star algebra and it just evaluates it at the identity. So this is only densely defined, but we had a discussion about how to deal with the fact that this is not defined everywhere. So this side exists basically for every f in here, but what I'm going to write down on the other side requires some hypotheses. And so what I want to do is I want to be in the part of the C-star algebra of G, which is the direct sum of all of these ideals coming from compact representations. So these are the operators which act as compact operators on each one of these L2 of G sigma spaces that we discussed before, and which will appear again here in a moment. So here's the formula. It's a kind of a crazy formula, and the sum will be over, what you call them, characters of the maximal torus T. Each time you have a character, you can do what? Well, you can take a character, and according to the theorem of Hermann Weyl, the Weyl character formula, you can take a one-dimensional irreducible representation of G, and you can associate to it an irreducible representation of K. Not exactly, because this map sometimes produces 0, but let's not worry about that just yet. So what I'm going to write down here is an irreducible representation of G, excuse me, of K, which depends on phi, and I'll remind you in just a moment what's going on. And I want to take that irreducible representation of K and tensor it by this spinor representation that we were discussing just a moment ago. And then I want to do this construction that we've looked at before. What I'm doing here is I'm taking this, which is a representation of K, not irreducible, and I'm converting this representation of K into a vector bundle over G mod K. That's one way of saying it. I'll remind you in just a moment. Like that. So I'll tell you more about what this is soon. And then one more thing needs to be put into this equation, which is a dimension, a numerical coefficient. And the numerical coefficient is going to be depending on phi, and it will involve some tau of phi like this. And so then there is an analytical formula relating traces. Some crazy thing. All right, so let's try and understand the bits and pieces here and see what we can make. Oh, and there's an overall constant. In my opinion, here is what the constant is. There's some Weyl group associated to some U. I have to tell you what that is, and some Weyl group associated to K. As I say, I'm at the moment, I cannot prove this except using Harish-Chandra's methods. And when you use Harish-Chandra's methods, it's very hard to keep track of what the constant actually is. But in the method I propose, the constant would be this thing here. All right, but let's try to understand the various bits and pieces here. First of all, U is the compact form of G. So U, like G, is a group of matrices. If G sits inside GLNR, then U sits inside GLNC, and U is always a compact group, so it's a group of unitary matrices. And it's characterized by the fact that its Lie algebra is K plus the square root of minus 1 times P. So you take the real symmetric matrices and you make them all skew adjoint by multiplying them by the square root of minus 1. These fellows are skew adjoint, and these are skew symmetric, so they're skew adjoint. So this whole thing is a Lie algebra of skew adjoint matrices inside of the unitary n by n matrices made up. And it corresponds to some compact group. If G was SL2, in fact, if G was SLN, this would be SUN. The equal rank condition implies that T, which is the maximal torus of K, is also a maximal torus of U. And so we can describe the irreducible representations of K and of U in the same way, using Weil's character formula, using characters of T. So this is the irreducible representation of K with character or quotations around that, given by Weil's formula, namely an alternating sum divided by some Weil denominator, as we discussed. That's a little too big. So we discussed Weil's character formula. I wrote down a general formula. Every example of a character in Weil's formula is always a fraction. There's a universal denominator and then some numerator, which is an alternating sum involving, of course, signs and permutations applied to the character phi. And let me just write it in this abbreviated form. Actually, this formula here may or may not be a character, because when you evaluate the identity, you're supposed to get the dimension of the representation, but it's possible you get a negative integer. It may be minus a character of a representation. The other possibility is that the terms in this alternating sum could cancel one another out completely, and then this would be the zero function. So this is not always an irreducible representation. It's either zero, or an irreducible representation, or minus an irreducible representation. If it's minus an irreducible representation, its dimension is minus the dimension of the associated representation. If it's zero, the dimension is zero. Those are the conventions. In other words, all I'm doing is I'm taking this function and I'm evaluating it zero. Except for the fact that we're supposed to be talking about tau there. But let me first say that S is this spin representation that we were discussing. And tau phi is again, the representation of U with character. Same thing, alternating sum of phi over the denominator, but now for U, not for K. And the terms, there are more terms in the alternating sum for U than there are for K, because it's the Weil group of U, a bigger group, which is responsible for the alternating terms. That's the formula of Harishchandra. And the reason you might believe this formula is that if you take the sum of all of these spaces, I forgot the dimensions. What you get is something very, very simple. You get, well, L2 of G. And then L2 of U tends to some finite dimensional representation lambda, and then you're supposed to look at the K-fixed part. And if you just look at the funny extra stuff, this stuff, this is exactly the space of all L2 forms, of all degrees, differential forms, on the space U modulo K. And This is the Hilbert space on which the Dirac operator acts, a certain Dirac operator whose index is the Euler characteristic. And indeed, the Euler characteristic at u modulo k is where this constant comes from. It's the size of the Weyl group of u divided by the size of the Weyl group of k. So this is this constant, whereas over there is the index of some operator, the Dirac operator, which is appearing thanks to this isomorphism. So we have something over here which is responsible for the Dirac index, and what's left is L2 of G, and that's responsible for the trace. That's the reason you might expect this to be true. I cannot convert that reason into a proof yet. That's work in progress with Tsuyoshi. This formula has some beautiful consequences, however. So it's a mysterious, amazing formula which was proved by Harishchandra in a purely analytical way, and not using operator theory, but just using function theory, harmonic analysis. Just reinterpreted here for the sake of Von-Kasparov conjecture. So these Hilbert spaces here are exactly the L2 Hilbert spaces as opposed to Hilbert C-star modules, the Hilbert spaces on which the Dirac operators act that I described earlier. I described the Dirac operators before as operators on Hilbert modules, but by changing the norms, by changing the completion operation, they also act as self-adjoint operators on these Hilbert spaces. And so we have appearing in this formula a hint of the Dirac operator. All of the Dirac operators which appear in Kohn and Kasparov's formula, they all appear also in this formula. All right. And oh, and I wanted to say something about this basic ideal. Where is it? All the way up there. The basic ideal is exactly the ideal of those operators in the C-star algebra of G, which act as compact operators on every Hilbert space which looks like this. Every one of these L2 of G sigma spaces, according to our basic theorem, involving our favorite picture, my favorite picture, according to the basic theorem, the basic ideal is exactly the ideal of functions f inside the C-star algebra which act as compact operators. That's why you can take the traces of them. And this formula tells us something very interesting when you reinterpret it in Dirac operator terms. Every compact representation, every discrete series, in other words, appears in the L2 kernel, some Dirac operator. Of the sort we were discussing before. These operators, I described them using C-star modules before, but they also are Hilbert space operators, and they have Hilbert space kernels, and those kernels are representations of G, and all of the compact operators appear in. Okay. And so, in some sense, the formula tells us that you found all of the discrete series. There they are. As long as you can solve the Dirac equation, in principle, you've found all of the discrete series, and I just want to develop that idea in the remaining minutes. Okay. In order to do that, to analyze the situation further, I need one algebraic idea. Which is another way of describing representations. It's called the infinitesimal character. So using this picture, we divided the C-star algebra of G into the basic ideal, so to speak, and the rest geometrically using the picture. And I want to describe a different decomposition which takes advantage of Harish-Chandra's formula and differential operators, but it's different. And for that, we get a little more serious about Lie theory, and we form the enveloping algebra. Of the Lie algebra of G. And then its center. Oh, okay, of course, a commutative algebra. So this thing acts wherever G acts through an algebra homomorphism wherever G acts, and it acts as scalars by Scher's lemma in representation theory in any irreducible representation of G. And the infinitesimal character, so in other words, for each irreducible representation, there's an algebra homomorphism from this commutative algebra to the complex numbers, which describes how this algebra acts on the vector space of any irreducible, of a given irreducible representation. And so this is an invariant you can attach to each irreducible representation. When the algebra is very simple, for example, for SL2R, this is a polynomial algebra in one variable, and you just have to say where the generator goes, and you get a single number. So in very easy cases, this invariant here so-called infinitesimal character can just be thought of as a number. But in higher rank situations, it's a more complicated thing. And so Harish-Chandra figured out what this algebra is, and I'll describe it using this idea of the compact form here. Well, here's one way of describing it. The first thing is it doesn't really matter whether you talk about G or the compact form of G. You get exactly the same Lie algebra. That's because when you form this algebra, you take the algebra over the complex numbers, the complex algebra of G. So the square root of -1 disappears, and the enveloping algebra for G is exactly the same thing as the enveloping algebra for U. You might as well complexify the Lie algebra before you do the enveloping algebra construction. And when you do that, you can forget about this I. You get one of this. So each time you have an irreducible representation of U, say finite dimensional, since U is compact, it gives an infinitesimal character. So if I have one of these phi's, which is the character of T, and I take its infinitesimal version, which is now a Lie algebra homomorphism from T, into the Lie algebra of U1, I get some character. And what you can check is very easy. It follows from Val's formula, is that the dependence of this character on phi is polynomial. In other words, if you fix an element in the center here and vary phi, what you get is a polynomial function defined initially just on this vector space, defined initially just on the lattice, but you can extend it. Okay, and what you get out of this is a map from the enveloping algebra of G to the polynomials on the vector space T. Okay. On this vector space, the Weil group acts of U, and all of the polynomials you get are symmetric under the permutation action of the Weil group of U. And in fact, this is an isomorphism. This is Harris-Chandra's theorem. So each time you have an irreducible representation of G, you get a new invariant, which is the infinitesimal character. I'm going to write it down here. That the infinitesimal character of any irreducible representation pi can be thought of, oh, sorry, this should have been the vector space dual of T, like this, can be thought of as an element of T star. Well, actually, T star, the complex version of T star, but modulo W. So there's a certain quotient of a vector space by a finite group, a certain affine variety there, and the infinitesimal character is a point in it, thanks to all of these correspondences. And the wonderful formula of Harris-Chandra, this one up here, let's just keep the wonderful formula and eliminate the details. The wonderful formula of Harris-Chandra tells us the following thing. It tells us where to find any compact representation. It tells us that every compact representation lies within some kernel of some Dirac operator. Well, you can calculate. It's a rather beautiful calculation, but I don't have time to do it for sure. You can calculate what is the infinitesimal character of any representation, which is the representation of G by translation on the kernel of a Dirac operator. You can just calculate it. And what you find is that the character agrees with one of these characters of finite dimensional representations here. And so you end up with the following rather beautiful consequence of Harris-Chandra's formula. So every discrete series, compact, these are synonyms, they mean the same thing, infinitesimal character, is the infinitesimal character of some actual, actual as opposed to fake. Remember we talked about the zero representation or minus a representation of some actual representation, irreducible representation of the group U. Here's another consequence. If you have an irreducible representation of G, and if it's not a compact representation, then at least it's induced from some compact representation, or maybe some compact modulo center representation. That was the basic theorem that we proved from this formula. And if you apply this fact not to G itself, but to some Levy, Levy subgroup, then you can calculate the infinitesimal character of any representation. What you find is that every non-discrete series projects. So what I want to do here, here's the complex vector space dual of T. And remember, the infinitesimal character is a point in this space, at least an orbit under W of this space. And I can project this onto its, it looks like its imaginary part, but people call it the real part, this part here. And what it projects onto is the, how did I write this? The infinitesimal character of some singular, let's call it, representation of so some. I mean, it's not actually a representation of U at all. It's an example of a character of T with the property that when you form this alternating sum, as I had written here, but then I erased it, you actually get 0. It's not a real representation of U, but let's call it a singular representation of U. I mean that when you form this alternation, which appears in the numerator of the character formula, you actually get 0, so it's not a real representation at all. Should have thought of a better name. That's by using this basic theorem of, other theorem of Harish-Chandra, this principle that if a representation is not discrete series, it comes by induction from some discrete series, and now you apply consequence number 1 again and do some calculation. So you have the following situation. Just going to squeeze in, I think, before time is up. Let's draw the picture for, well, let's draw a reasonably interesting example here. This is the picture for SP4. And inside of SP4R, there is some lattice. I'm not going to be able to draw very well, something like this, of potential, what should we call them, bioparameters, potential phis which appear in this formula. And they all sit in one orbit like this. So these ones here, which are regular, which are not on any wall, what I'm drawing here is a picture of the vector space of homomorphisms from the maximal torus inside of SP4 into I times R, some two-dimensional real vector space, and the red dots correspond to the irreducible representations of U, of the group U, which is the symplectic, compact symplectic group, the group of quaternionic unitary matrices. And the discrete series have infinitesimal characters, which are exactly these points here. Okay. What I've drawn is one fundamental domain for the action of this Weyl group. As for other representations, well, they don't necessarily have infinitesimal characters which lie in this plane, because this is just the real part, if you like, of a complex two-dimensional space. I didn't have room to draw C2, the complex two-dimensional space. I only drew R2. So coming out of this picture are two more dimensions, but when you project onto this real space, what you find is that the infinitesimal characters have to lie here, thanks to the wonderful formula of Harish-Chandra. And what you notice is that they're disjoint. They're disjoint. No projection of a discrete series ever agrees with any projection of a non-discrete series. And so you can separate the representation theory of G, the tempered representation theory of G, into two disjoint pieces using blue and red chalk, using infinitesimal character, as opposed to using geometry, which is what we used before. Okay. Of course, this is only after you know a great deal of information, which we proved using the geometry. We proved this Harish-Chandra principle using this picture. But here's a way of expressing some similar idea algebraically. The discrete series live here, and the red dots are completely disjoint from the blue dots. There's no overlap whatsoever. And what arises from this picture, I'm going to have to say a few more words about this next time, because I have only 4 minutes today. I want to go back now to to the Kasparov map. And I want to imagine taking this map and dividing it into two, into, so to speak, a compact part and a non-compact part, into a singular part and a non-singular part. Oh, and now I need to, this is a picture of T star modulo the Val group of U, but what's interesting for the representation theory of K is T star modulo the Val group of K. And the Val group of K is generated just by flipping across this line. So now I have to include more dots here. So there should be a line down here, shouldn't it? Like this. So each one of the dots I'm now attempting to draw, not the ones on this line, but the ones away from this line, corresponds to an irreducible representation of K. These here are representations of K, which are singular from the point of view of U. And so these dots, which correspond to representations of K, do not correspond to representations of U. They freely generate this sum end of the left-hand side. The rest, which are not circled, generate this side here. And in a similar way, you can break up the right-hand side into the C-star algebra of G, like the non-basic part. Direct sum, the basic part, basically. I lied, but one didn't lie. I omitted some crucial statement, which is written on the board now, which is that the entire basic ideal is actually complemented inside the C-star algebra. That's the result of, that's also a consequence of Harris-Chandra's formula, so-called uniform admissibility. And this separation, which I've described here, tells you that the Kasparov map respects this decomposition. So the only way you can attempt to understand, the only way you're going to get parameters for discrete series is from, did I do it the right way? Yeah, from the non-singular part of R of K. And the only way you're going to get parameters for this K theory is from the singular part. It falls apart very obligingly into a direct sum of two pieces like this. And then I'll say more about this next time. A final ingredient for the analysis of the discrete series is a wonderful theorem of Kasparov, which does something kind of incredible from a representation theory point of view. Oh, here it is, it's still up here. It's a theorem, turned out to be a theorem eventually, that the index map of Kohn and Kasparov is an isomorphism. That is this basic Kohn-Kasparov isomorphism. Before the theorem was proved, Kasparov built a sort of dual index map, or so-called dual Dirac map, going the other way. There's a map going the other way. This is very hard to describe from a representation theory point of view, but it's very easy from a geometric point of view. And it's very easy. So the theorem which says that these two maps are mutual inverses is very hard. But the theorem which says that if you do the Kohn-Kasparov map and then you do the Kasparov map, that you get the identity over here, this is very easy. This is very easy. This is a basic calculation which you see again and again and again in K theory. So Kasparov proved that his dual Dirac map is a one-sided inverse to the map of Kohn and Kasparov. And as soon as you've understood that the index map of Kohn and Kasparov respects this decomposition, it's very easy to check that the second factor is an isomorphism. by an argument that I'll talk about next time. So we're trying to understand, today, we're trying to understand the discrete series. The fundamental tool to do that is a strange analytical identity involving traces, different sorts of traces. Here's some strange trace whose values correspond to these mysterious formal dimensions of discrete series. Here it's the ordinary operator trace. And they're all connected by this marvelous formula of Harish-Chandra, which maybe has something to do with index theory and the Dirac operator. Fine, now you start to analyze this formula, and what you notice is that algebraically you can perform a separation of the left-hand side, just as geometrically you can perform a separation of the right-hand side. Using the infinitesimal character, you can reconcile, you can match those two separations, and you can prove that the map of Kahn and Kasparov is diagonal. And then it's a very easy step, a small step from there, using Kasparov's theorem to show that the second factor is in fact an isomorphism. And therefore, the discrete series correspond exactly to non-singular parameters, the dots in this picture to the lower side of this diagonal line, which do not lie on any line. Those are the discrete series. And as for these mysterious singular ones, not the ones on this line, that was a mistake to draw them. Now, as for the blue dots, these correspond to something that we don't understand yet. We don't understand in this lecture yet, because they correspond to this mysterious non-basic part of the C-star arch. All right. I think it's time to stop, so thank you very much.
Any question or comments? So how do you understand the singular part?
So what I'll do next time is try to answer that question. In order to understand the singular part, you need to understand more about this operation of transconduction. You have to understand something about the structure, as far as I understand it, of this non-singular or non-basic part of the C-star algebra. At the moment, my understanding is not very good. And so I will show you a calculation next time, which is the beginning of understanding this isomorphism. But one hopes that there's an elegant argument using Kasparov's theorem, which will easily prove that the second component, the singular component of the Kahn-Kasparov map, is also an isomorphism. I would like to say the singular component is an isomorphism for a relatively soft reason. Something like this formula of Harish-Chandra, which you can apply to a Levy subgroup, should tell you, and then something like this argument, which I'll describe next time, should tell you that the singular part of this map is an isomorphism as well. At the moment, I cannot do that. I can just do explicit calculations using detailed knowledge of what the C-star algebra looks like. And so, okay, that's a gap. I don't know how to do that yet. But in the end, one would hope that this formula tells you everything. My hope is that this secret formula of Harish-Chandra will open up the whole story. And then if you use a little bit of topology, like the theorem of Kasparov, then you can help understand the representation theory using some K-theory techniques.
So this singular are just like a virtual foundation, which is zero?
Yeah, I mean, these are representations. I mean, they're not really representations. You can apply the Weil character formula to any unitary character of the maximal torus. And, of course, you don't really get a representation unless the character has some characteristic properties. It should be the non-zero function, and it should be positive on the identity element. So the singular part corresponds to representations which violate the first condition. These representations are actually zero. If you nudge them a little bit, then they're not zero. They're actually positive on the identity element, but they're not.
But they are the subgroup of the representation ring?
Yeah, of K, not of U, but of K.
Oh, okay.
These are representations which you cannot see from the. They correspond. If you have a dot in this picture, you can convert it into a representation of K, which can be an actual representation. That's what we're talking about here. But some of these dots, which are actual representations of K, are not actual representations of G, like this one, of U. They correspond to the zero representation of U. So these are actual representations of K, which give, using the Val character formula, the zero representation of U. Sorry about that.